an AI-generated post for your viewing pleasure. Transforming language models. The power of BAM and mixture of experts. What if the secret to unlocking the next generation of super-efficient language models lies in how we leverage existing knowledge? Researchers have unveiled BAM, Branch, and Mix, a revolutionary step forward in the mixture of experts architecture that could redefine how we upcycle dense models into powerful, specialized AI. Before we jump into the details, let's set the scene. In the rapidly advancing field of artificial intelligence, the pressure to create more capable and efficient language models has never been higher. Let's take a closer look at a fascinating new paper that tackles these issues head-on. In an era where artificial intelligence is slowly creeping into every aspect of our lives, enhancing the efficiency of language models has become a top priority for researchers and developers. One groundbreaking paper has introduced a new method called BAM, or Branch Attend Mix. This approach promises to transform how we utilize existing neural network architectures, particularly in the realm of natural language processing and understanding. As we push for more advanced AI capabilities, traditional models face critical challenges such as increased computational costs and training instabilities. The research behind BAM offers an innovative solution for overcoming these hurdles by effectively combining what we already know from dense models with new strategies and mixture of experts architecture, giving us the potential to boost performance and efficiency in AI applications. To follow along, it's important to understand a few terms. Mixture of experts, MOE, is an architecture where only a portion of the model parameters are activated for a specific task, which helps in reducing computational load. In BAM, researchers propose a unique way to upcycle these models by not only leveraging feed-forward network, FN, parameters, but also tapping into the powerful attention mechanisms within these architectures. Attention mechanisms are a crucial part of modern language models, allowing the system to weigh the importance of different input tokens when making predictions. BAM uses a technique called soft routing, allowing each input to connect with all attention experts rather than being limited to a handful. This innovative approach informs how models can be structured to achieve optimal results across a range of tasks, significantly enhancing their capability and adaptability. Now that we've introduced BAM and established some key concepts, let's dig deeper into the technical contributions made by this exciting research. First off, let's break down the core contributions of BAM. Traditional language models often rely solely on dense architectures, where each parameter is applied to every input, making them costly and inefficient. BAM addresses this challenge by employing a mixture of experts, MO architecture, which activates only a subset of parameters at any given time. What sets BAM apart is its unique process of initialization, where it not only utilizes the feed-forward network, FN, parameters from pre-trained dense models, but also fully integrates attention parameters. This dual upcycling approach taps into the specialized knowledge embedded in existing models, allowing BAM to stand on the shoulders of giants. By fully utilizing these specialized dense models, BAM maximizes their capabilities, revealing that existing models can provide valuable expertise that enhances performance in new architectures. Additionally, BAM employs a parallel attention transformer architecture that enables simultaneous computation of attention and FN experts, enhancing overall efficiency, a crucial aspect given the scale of modern language tasks. This architecture's ability to leverage concurrent computation offers exciting new possibilities for multitask learning, similar to how ensemble methods function, but within a single MO setup. As BAM balances multiple processing streams effectively, we could see advancements towards models that adapt well to distinct real-world scenarios. However, it's essential to note that the BAM method, despite its promising advancements, lacks extensive empirical comparisons with existing state-of-the-art models, particularly those recognized as leading methods in the field. The paper primarily references BTX as its baseline for evaluation, which raises concerns about the breadth of its comparisons. Without testing against a wider array of models, the robustness of BAM's performance claims remains questionable. The experiments conducted focus mainly on perplexity and downstream tasks, Yet the complexity and diversity of domain-specific tasks are not adequately represented. This could mislead readers into overstating BAM's versatility across various applications. Although the authors mention improvements compared to BTX, they do not sufficiently address how BAM stacks up against other advanced MO architectures that may incorporate similar or different techniques, potentially leading to an incomplete assessment of BAM's true capabilities. Moreover, as we explore the architecture of BAM, we must consider its reliance on pre-trained dense models. Leveraging these models can enhance performance and efficiency, but it also raises concerns about the perpetuation of existing biases embedded within those models. The paper mentions the advantages of using pre-trained models to mitigate costs and instabilities, but it doesn't thoroughly address how these biases might be amplified in the BAM architecture. This oversight raises ethical questions regarding real-world applications, particularly in sensitive areas such as law, healthcare, and education. The lack of a concrete strategy for auditing or alleviating biases present in dense models is a significant gap, which must be addressed to ensure that BAM and similar architectures contribute positively to AI development. Additionally, the ablation studies conducted in the BAM paper provide some interesting findings, but they ultimately lack the depth needed to fully demonstrate the architecture's key contributions. The focus on parameter matching between BAM and BTX misses the opportunity to explore the multidimensional interactions within BAM's architecture in real-world applications. The reliance on quantitative metrics can obscure the qualitative impacts of upcycling attention experts, leaving the interpretability of results limited. Finally, the study does not adequately consider external factors that could affect performance, such as data variability and the diversity of training sets. The simplistic adjustments made to configurations do not reflect the real-world intricacies that BAM might encounter when deployed across various applications. This limits our understanding of BAM's practical utility. Having discussed the key contributions of BAM, let's explore how this innovative approach fits into the existing research on language models and what it might mean for the future. Now, how does BAM fit into the current research on language models? Previous efforts such as BTX initiated attempts at upcycling models, but largely overlooked the attention parameters, which are vital for high-performance outcomes. BAM's ability to leverage these parameters reveals an unexplored avenue in model design, emphasizing the untapped potential within existing structures. In addition, BAM's emphasis on soft routing for attention experts stands to challenge traditional routing methods in MOEs. By allowing each input to connect to all attention experts instead of limiting them to top K, BAM stabilizes training and elevates overall performance. This realization could inspire researchers to reconsider how we assign and partition resources in future architectures, granting more flexibility to cater to various input characteristics. As BAM consistently outperformed BTX in empirical evaluations across various tasks, it raises questions about what our metrics for model success should truly be. Moving forward, success may not always be about sheer parameter counts, but rather how we can leverage the collective strengths of diverse models. In doing so, we might also foster an environment that encourages innovative collaboration and cross-disciplinary engagement, unifying efforts across fields to create more capable, well-rounded systems. In conclusion, BAM emerges as a trailblazer in the field of language models, combining efficiency with advanced performance through innovative use of existing parameters. The dual focus on FN and attention layer integration represents not just an enhancement of model capabilities, but a shift in our philosophical approach to AI development. As key players in AI research take these findings to heart, we might witness a new wave of adaptable, efficient models that respond to real-world applications more effectively than ever before. So if you're as excited about these advancements as we are, make sure to give us a thumbs up and subscribe for future updates. Share your thoughts in the comments below. How do you envision the future of language models? Could BAM be the breakthrough we've been waiting for? Let us know what you think.